These are notes for AP Calculus on the topic of relative, which are also called local extrema. So, relative or local extrema, they refer to both the relative local maxims and the relative local minimums of the function. And relative and local are used interchangeably here, so they mean the exact same thing. So let's look at this graphically first. Let's look at relative or local maximums first. So they're called relative or local. You can see there's one right here on this graph, because relative to the points or locally to the points on either side of it, these have a maximum y value, a higher y value than the points on either side. And you can see this one has a relative maximum right here, and this graph has a relative maximum right here. So you can think of relative maximums being like on the top of a hill or a mountain. So let's see what's happening with the first derivative and what that tells us about the original function. Let's draw a number line for each of these. So here this shows up until x equals 1. Well, if we take a look at our first derivative, think of like a tangent line along here. The tangent line here, these would all have positive slopes, right? So the first derivative here, f prime, would be positive. Until right at 1, you can see the tangent line there would be horizontal, so it would be 0. Would be the derivative. So remember, the derivative represents the slope of the tangent line. And then afterwards, you can see all the tangent lines would have a negative slope, so the first derivative would be negative. And that shows us that f of x, the y values here, you can see from left to right, they're increasing. And then from left to right, now the y values are decreasing. Let's take a look at the next one here. The next one, our relative maximum, is at x equals -1. But this time, you can see we've got a cusp here with an abrupt change in the slope, so the derivative would be undefined. You wouldn't be able to find the tangent line right at that point. But again, you can see up until that point, these are all positive slopes of the tangent lines that go along here. So the first would be positive. And right here, the slopes here, these are all negative slopes. So the first derivative would be negative. And again, though, we can look at the y values and see, okay, well, the y values from left to right are increasing here, and they're decreasing here. And our last one, graph of relative max, this one's at x equals 3. Again, we've got an abrupt change in the slope of corner there, so the derivative would be undefined. But again, the slope from the tangent line up here, until 3 would be positive. Slope afterwards, first derivative would be negative. And again, you can see f of x would be increasing in the decreasing. Now let's take a look at graphically what relative or local minimums look like. So these are points that are relative or locally compared to those that are lower, have a lower y value than the points on either side. So here we can see we have a relative local minimum right here, on this graph right here, and on this graph right here. So again, let's draw our number line underneath each of these. You can see on this one it occurs at -2. Right at -2, you can see the slope of derivative is 0 there. But up until then, the tangent line has a negative slope, so the first derivative would be negative. After -2, you can see all these would have positive slopes for the tangent line. Then this one right at 0, we've got a cusp, so an abrupt change of the slope, the first derivative is undefined. But up until that point, these slopes of the tangent lines are all negative. Afterwards, slopes of the tangent lines will all be positive. And on this one at 1, you can see we've got a corner there, an abrupt change of the slope, so we can find the derivative right there, so it's undefined or doesn't exist. And up until that point, the slopes are negative, and then afterwards the slopes are positive. And again, what this shows us about the original function f of x is the y values here are decreasing, and the y values from left to right are increasing. Again, decreasing, y values increasing, decreasing, and then increasing. So let's see what we can figure out about how to find these relative and local minimums and maximums, relative and local extrema. Well, let's first look at critical numbers. Look at where all those occurred. They either occurred at where the derivative was 0 or undefined. Either 0 or undefined. So those are what are referred to as critical numbers. are the x values where the derivative is 0 or undefined. And the reason why they're called critical, I think critical meaning important here, these are the places that relative or local extrema could occur. Doesn't guarantee we're going to have one, but these are the places where we could have it. So let's just get practice first of all, finding the critical numbers of the function, finding the x values where we might have a local min or max. So you start by finding the derivative. In this case, f prime of x would be 4x cubed plus 12x squared plus 8x. And then figuring out what x values make the derivative 0 or undefined. Well, in this case, there's no denominator, so it won't be undefined, so we just have to figure out what makes it 0. And what would help us here, if we factor out the GCF of 4x, that leaves us with x squared plus 3x plus 2. And that factors further into x plus 2 and x plus 1. And then one of these has to be 0, so either the 4x equals 0, x plus 2 equals 0, or x plus 1 equals 0. This one gives you x equals 0, this one x equals -2, and this one x equals -1. So those are our critical numbers. And you can write a bracket formula. We got 3, we got -2, -1, and 0. So these are the 3 x values where we might have a local minimum or a local maximum. Doesn't guarantee there's one, but these are the only x values where there might be one. All right, let's take a look at one more that's a little bit more complicated. On this one, the first thing to do is rewrite this. So the square root of x is the same as x to the 1/2. And then we have this 2x minus 4. That whole thing is raised to the 4th power. So you can see overall in this one, since we have x to the 1/2 times 2x minus 4 to the 4th, big picture we're going to be using the product rule. So we take the derivative, f prime of x. The product rule, the first thing we have is the derivative of the first function, so that would be 1/2 x to the -1/2 times the second one as it is, 2x minus 4 to the 4th, and then plus, for the product rule, the first one as it is, x to the 1/2 times the derivative of the second one, and since we have a function inside there of 2x minus 4, we'll also need to change all of this. So on the outside, we'll be using the power rule. So we bring down the 4, and then it'll be 2x minus 4 cubed. But the chain rule says we also need to multiply by the derivative of the inside, which in this case is 2. Now, to figure out all the places that make this 0 undefined, if you try to leave it like this and figure that out, it's going to be pretty difficult. So what we can do, we think about this term, since these are all multiplied as our first term, plus, this is our second term. The way to make this a lot simpler is to use factoring. So the first thing you always look for in factoring is the greatest common factor GCF. So what do these have in common we could factor out? Well, we've got x to the -1/2 here and x to the 1/2 here. So remember, whenever you're factoring, you factor out to the lower exponent. Just like if you had x squared, you can see over here, we have x cubed, x squared, and x. We factored out the lowest exponent of x to the first. Here, the lowest exponent x to the -1/2, so let's factor that out. But we also have in common 2x minus 4. This one has 2x minus 4 in the 4th. This one has 2x minus 4 in the 3rd, so we factor out the lower exponent, which is 2x minus 4 in the 5th. And then we put down what's left of each term. Well, what's left this term we still have is 1/2. We didn't factor that out. The x to the -1/2, that's completely gone. Let's factor that in. Well, we had 2x minus 4 to the 4th. We factored out 3 of them, but there's still going to be 1 left. So that's times 2x minus 4. And then plus, let's see what's left of our second term. We still have the 2 times the 4. That's 8. And this 2x minus 4 cubed, that's completely gone factored out. But we had x to the 1/2. The part that might be the trick is figuring out what's left of that. So x to what exponent would be left? Well, let's think about this. If we were to multiply this back out, these exponents, the x to the -1/2 and this exponent would have to add, we'd add them up, and it would have to give you 1/2. Back what we had together. So what could we add to negative 1/2, that would give you a positive 1/2. Well, first way you might think about it, well, that would have to be 2/2, right? Because 2 over 2 minus adding to negative 1 over 2 would give you positive 1 over 2. But 2 over 2, that's just 1. And oftentimes this happens where the exponent, when you factor out a fractional exponent, the exponent that's left is oftentimes an integer. So now let's keep simplifying this. So now that this is factored out with a negative exponent, that now allows us to move that to the denominator. And if we switch it back to radical form, that'll be the square root of this. So that's the 1/2 down here, which stays that. The 2x minus 4 cubed stays where it is. And then let's go ahead and simplify what's left inside the parentheses. So first, notice these are both divisible by 2. So if we distribute out the 1/2, 1/2 times 2x is just x. 1/2 times negative 4 is negative 2. And then we can combine x minus 2 plus 8x. That's going to give us x plus 8x is 9x. And then minus 2. And now, this one has a fraction, so this one could be 0 or undefined. To figure out where it's 0, you set the numerator equal to 0. To figure out where it's undefined, you set the denominator equal to 0. So if we set the numerator equal to 0, this cube doesn't really affect what makes it 0, just what's inside there. So if we set 2x minus 4 equal to 0, you can see we get x equals 2. If we set 9x minus 2 equal to 0, we'd add the 2 divided by 9, we get x equals 2/9. And here, if we set the square root of x equal to 0, again, what matters is what's inside there. If that x is 0, the square root of that's going to be 0. That would just give you x equals 0. So those would be our 3 critical numbers here. The 3 places where we might have a local or relative minimum x. The x equals 0, 2/9, and 2. Now let's take a look and see if we can figure out some more besides just where the critical numbers are. So what we're going to be using is the first derivative test. So let's go back to those graphs here and figure out what would cause a graph to be increasing or decreasing. If you look back to both of these, we can see, well, when the first derivative is negative, that indicates a negative slope, so the function would be decreasing on both of these, right? There's negative is decreasing. And when the first derivative is positive, you can see that means the slope is positive, so the function must be increasing. Okay, first derivative positive, the function is increasing. So with our first derivative test, intervals in which the first derivative f prime of x are greater than 0, in other words, positive, indicate the function is increasing. Intervals in which the first derivative is less than 0, negative, indicate the function f of x is decreasing. And now let's look at how we can tell at these critical numbers whether we have a local minimum or a local maximum. Again, if we go back to our graphs, let's see what all the local relative maximums have in common. Well, the first derivative on those changed from positive to negative. That's what made it a local maximum. As opposed to the local minimums, the first derivatives changed from negative to positive at all the local minimums. So that's how we're going to be able to tell when we don't have the graph whether at a critical number it's a local minimum or a local maximum. If the derivative function changes from positive to negative at a critical number, there's a relative, also called a local maximum at that critical number, as long as the function is continuous there. And if the derivative function changes from negative to positive, though, at a critical number, there's a relative, or also called a local minimum. At that critical number, assuming again the function is continuous. So now let's go beyond just finding the critical numbers. And here we're going to find the increasing and decreasing intervals of the function and find the coordinates of all the relative extrema and identify each as a relative minimum or a relative maximum. So we first need the first derivative, just like we're finding the critical numbers. We still have to do that first. Here the first derivative would be 4x cubed minus 16x In this case, that will never be undefined, so we just need to figure out where this is 0. You would factor out 4x as a GCF. You'd be left with x squared minus 4. And then you can use difference of perfect squares factoring to factor the x squared minus 4 into x minus 2 and x plus 2. So our critical numbers would be from the 4x, x equals 0, from the x minus 2, you get x equals 2, and from the x plus 2 equals 0, you get x equals negative 2. But now we're going to go beyond just find the critical number. We're going to next draw a number line. We don't have the graph of it. This is going to tell us what's happening in the graph. And then mark down, okay, our 3 critical numbers, or put them in order, negative 2, 0, and 2. And then label this f prime of x. And all of these made the first derivative equal to 0. These are exponents. So then we just have to test in between them to see if the first derivative is going to be positive or negative. And you could test in any form of the derivative, but usually the completely factored form tends to be the easiest. So if you test negative 3 makes this times 4 makes this factor negative. Negative 3 minus 2 is negative. Negative 3 plus 2 is negative. 3 negatives multiply together, it's going to give you a negative. Then between negative 2 and 0, you could test negative 1. Negative 1 times 4, that's negative. Negative 1 minus 2 is negative. Negative 1 plus 2 is positive. 2 negatives times a positive is positive. Between 0 and 2, you can test 1. 4 times 1, that's positive. 1 minus 2 is negative. 1 plus 2, positive. 2 positive times a negative is negative. And greater than 2, you can test 3. 3 times 4 is positive. 3 minus 2 is positive. 3 plus 2 is positive. 3 positive numbers multiplied together is positive. So this shows us a couple things about the original function f of x. It shows us, this is the slope, where the first derivative is negative, the original function must be decreasing. Where the first derivative is positive, the original function must be increasing. And then back to decreasing, and then back to increasing. So we can answer the first part of the question, to find the increasing and decreasing terms of the function. So let's go ahead and write that down. Let's say f, and then we start with the other one, is increasing. When you're talking about intervals, you use on, from negative 2 to 0. And then there's another interval, so put on the u for union. And then from 2, keeps on going right forever, to infinity. And then we can say f is decreasing on, so it goes to negative, from negative infinity to negative 2, and with 0 to 2. Now, not all mathematicians or even textbooks agree on whether at these endpoints here, other than the infinity and negative infinity, whether they should be using parentheses or brackets when you're writing down intervals. So actually either one would be considered correct. So if you use brackets on the negative 2 and 0, that would also be correct. Okay? But to me it makes more sense to use parentheses because technically at those points the function is not increasing or decreasing. But brackets would be correct for all these except you would never put brackets on infinity or negative things that are not actual numbers. Now, the other thing this tells us about, it also shows us where we have local minds and maximums, relative minds and maximums. So if the function goes from decreasing to increasing, the first order changes from negative to positive, that's going to be a relative minimum at that critical number. But if the first derivative changes from positive to negative, if it goes from increasing to decreasing, that's going to be a relative maximum. And then at 2, we've got decreasing to increasing. First derivative goes from negative to positive, so another relative minimum. So we have 3 critical numbers. In this case, 2 of them are relative minimums and 1 is a relative maximum. But notice it said find the coordinates. That means we also need the y coordinates. So to find the y coordinates, you would just plug them back in the original equation. So if you plug in, let's start with 0. You plug in 0, that wipes out everything but the 1. Okay. So we can say f as it refers to it as relative maximum, so a relative maximum And when you're talking about a point, you don't use on, you use at. At x is 0, y is 1, so at the point 0, 1. And for the minimum, those are 2. Normally I would plug in 2 and negative 2 separately. However, what I notice is this is an even function. All the x1s are even. So actually you can plug them in simultaneously, plus or minus 2, because it's an even function. Because then you'll have plus or minus 2 to the 4th minus 8 times plus or minus 2 squared plus 1. Well, whether it's positive 2 or negative 2 to the 4th, either way that's going to be a positive 16 minus 8 times negative or positive 2 squared is going to be 4 plus 1. So that would be 16 minus 32, 8 times 4, plus 1. That's 17, 16 plus 1 minus 32 is negative 15. So that's the y-coordinate for both 2 and negative 2. So we can say F has relative minimums at negative 2, negative 15, and 2, negative 15. So that answers everything they're asking. So the first derivative tells us not only whether the function is increasing or decreasing, but also whether those critical numbers are actually minimums or maximums, or sometimes they can be neither. We'll see. All right, let's take a look at the next one. This one, the first thing to do is rewrite this out of radical form into fractional exponents. So the first one you could write as x to the 4/3 plus 4x to the 1/3. So that's still the original function. Now let's take the derivative of g prime of x. Derivative of x to the 4/3 would be 4/3 x to the 1/3, then plus 4 times 1/3 is 4/3, x to the, subtract 3/3 from that, we give you negative 2/3. And then to see all our critical numbers here, it's probably easiest if we factor out the GCF. So you can see here's your first term, plus here's your second term. What they have in common is 4/3, we can pick that up. And x to the lower x one is negative 2/3. And now let's see what that leaves us with. Well, the first term, the 4/3 is gone, and we had x to the 1/3. So it would be x to the what? Well, again, this exponent here, and negative 2/3 have to add up to be 1/3. So you can see that would have to be 3/3. Because 3/3 and negative 2/3, that would be 1/3. But what's 3/3? Well, 3/3 is just 1. So that's just x to the first term, just x. Plus, what's left of this term? Well, we factored everything out. So all that's left is a 1. And then if we simplify this, we got a 4 on the numerator, 3 on the denominator, and now that this is factored out, we can move this x to the negative 2/3 to the denominator. So it becomes, in radical form, the cube root of x squared. And then here we just have x plus 1. So remember, the critical numbers are where the derivative is 0 or undefined. In this case, it's the has a denominator. So you said the numerator equals 0 and the denominator equals 0. So that would give us critical numbers. In the numerator, we get negative 1. And for the denominator, what makes that 0 would just be 0. So let's go ahead and put those on the number line. Got negative 1 and 0. And then we can label this g prime of x. Well, negative 1 came from the numerator, so that makes the derivative 0. But 0 came from the denominator being 0, that means that's where the derivative is undefined. So at that point, we've got like a corner right across. Alright, so now let's go ahead and test negative 2. And when we're testing, sometimes you can find some shortcuts, make it a little easier. We're testing the whole derivative here. But notice this is squared, so you don't have to worry about that ever being negative. So you really only have to worry about the numerator, being positive or negative. So if you test negative 2, that makes the numerator negative. In between negative 1 and 0, that's negative 1/2. Plus 1 is positive. Greater than 0, you get as 1, 1 plus 1, positive. So this shows us our original function, g of x. And the first derivative negative would be decreasing, then positive would be increasing, and then positive still increasing. So that means we've got, the first write down intervals, it's increasing, decreasing now. The g is increasing on -1. Now, because it's undefined, whenever it's undefined, you have to stop your intervals. So if it was 0, we wouldn't have to stop it. It's undefined, so -1 to 0, and then a union with from 0 all the way to infinity. And g is decreasing on from -infinity all the way to -1. And let's see if our critical numbers actually are mins or maxes. Well, at -1, first derivative changes from negative to positive, decreasing, increasing. So that's a relative or local minimum. But at 0, notice the first derivative doesn't change sign, it stays positive. So even though that's a critical number, it doesn't turn out to be a min or a max in this case. And then we just need the y coordinate -1. So when you plug in -1 in the original function, g of -1. Here it's probably easier to use the radical form. So the cube root of -1 to the 4th plus 4 times the cube root of -1. Well, -1 to the 4th is just 1, so that's a cube root of 1. And then the cube root of -1 is -1 times 4 gives you -4. Cube root of 1 is 1 minus 4 gives you -3. So there's your y coordinates. We can say g as a relative minimum at -1, -3. Take over the next example here. On this one, you take the derivative, you can see we have a function inside, so we have to use the chain rule. So h prime of x, using the power on the outside, would be 3, 2x minus 3 squared. But the chain rule says we have to multiply by the derivative inside, which is 2. And I'm going to pull the 2 out in front with a 3, so we get h prime of x equals 6, and then 2x minus 3 squared. So we want to see what makes this 0. If we said, well, 6 can't be 0, there's just 6, there's no x's out there. So if we said the 2x minus 3 equals 0, this time we only get one critical number of 3 halves. So that's the only place we might have a local minimum x. To see if it is, again, we test the number line. In this case, there's only one critical number, just 3 halves. Let's test h prime of x. 3 halves makes the derivative 0. So over here we could test like 0, but notice we got this squared here. So other than 3 halves, anything else we test in this is going to be positive. So you can test 0, but that's going to be positive. You can test something over here like 5, but that's also going to be positive. So what this shows us is that h of x is increasing and then still increasing. So if it's at h is increasing, and right here it's 0, so it's increasing on from -infinity. You could stop at 0, but because it's just 0, not undefined, you don't have to. You could just say from -infinity all the way to infinity. And this is a special type of function. When a function is always increasing or always decreasing, it has a special name. It's called strictly monotonic. So this is an example of a strictly monotonic function. So strictly monotonic function that is always increasing, like this one is, or could be always decreasing. And in terms of relative mins or maxes, 3 halves was only a possibility, that's only the number, but since the set first derivative doesn't change sign, h has has no relative extrema. Extrema refers to both mins and maxes. Okay, now let's take a look. The next one say just find the x coordinate of each local min or max. So here we're not going to need the y coordinate. The difference here is we're going to justify our answer. So you can see on this one, to take the derivative, we would need to use the quotient rule. So for f prime of x, we start by the derivative numerator, which is 3x squared, times the denominator as it is, x squared minus 3, minus the numerator as it is, x cubed, times the derivative denominator is just 2x. And all divided by the denominator as it is squared. And let's go ahead and simplify this. So here, you could factor, but it might be easier to just distribute out in this case. That's going to be 3x to the fourth minus 9x squared, and then minus 2x to the fourth. But the denominator, squaring that out is not going to make it simple, so I'm just going to leave that as x squared minus 3 squared. Keep going. 3x to the fourth minus 2x to the fourth is just x to the fourth minus 9x squared over x squared minus 3 squared. And we can keep factoring that numerator. Take out a GCF of x squared. We do with x squared minus 9. And you can see we've got difference of perfect squares. So we can keep factoring it. So x squared and then x minus 3 and x plus 3. On the numerator, and the denominator, x squared minus 3 squared. So now that we have it simplified in factored form of a single fraction, you can find the critical numbers by saying the numerator equals 0 and the denominator equals 0. Get all of our critical numbers. So for the critical numbers, we said the numerator equals 0. What we get from the x squared, you get x equals 0. From the x minus 3, you get 3. And from x plus 3 equal to 0, you get negative 3. And from the denominator equal to 0, we said x squared minus 3 equals 0. You could add the 3. And then take the square to both sides. So we get x equals plus or minus 43. So we actually have 5 critical numbers here. So let's put them all on our number line. In order from lowest to highest. Equals f prime of x. Let me just move this up a little bit. Okay. So I've got negative 3, negative square root of 3, which is like negative 1 point something, 0, positive square root of 3, positive 1 point something, 3. My weird number on it, f prime x. So negative 3, 3, and 0 all came from the numerator, so those all make the derivative 0. Plus or minus root 3 came from the denominator, that just makes the derivative undefined, or doesn't exist. So now we just have to test between them. Let's see if we can find any shortcuts before we start testing. Well, notice we've got a squared here, so that's going to be positive, and a squared there. So the only thing we have to test is really the x minus 3 and the x plus 3. So if we test negative 4, negative 4 makes this factor negative. Negative 4 plus 3, also negative. Negative times a negative is positive. Between negative 3 and negative square root of 3, the easiest thing to test there would be negative 2. Negative 2 minus 3 is negative. Negative 2 plus 3 is positive. Negative times a positive, negative. Between between negative square root of 3 and 0, you can test negative 1. Negative 1 minus 3 is negative. Negative 1 plus 3 is positive. Negative times positive. Negative. Between 0 and square root of 3, you can test 1. 1 minus 3 is negative. 1 plus 3 positive. Negative times a positive is negative. Yeah, that's right. And then between square root of 3 and 3, you can test 2. 2 minus 3 is negative. 2 plus 3 positive. But it's still negative. But then here you can test 4. 4 minus 3 is positive. 4 plus 3 positive. Positive times a positive is positive. So you can see this shows us that f of x would be increasing, decreasing, still decreasing, still decreasing, still decreasing, and then finally back to increasing. So we could write the increasing and decreasing intervals down, but that's not what it asks for. It just asks for the local mins and maxes and just the x coordinates. We just have to justify it. So let's look at each of the critical numbers. Negative 3 is the first order changes from positive to negative, increasing to decreasing, so that's a relative max. At negative square root of 3, the first derivative doesn't change sign, so that's neither, it stays negative. At 0, the first derivative doesn't change sign, that's neither, it keeps decreasing. At positive square root of 3, again, the first derivative doesn't change sign, it stays negative, so that's not either. And then at positive 3, it goes from decreasing to increasing, so that's a relative. First derivative changes from negative to positive. So we had 5 critical numbers, but only 2 of them turned out to be local extrema after all. So, let's say f as a, now here it refers to it as a local, so I'm going to do that in my answer. Same thing as relative, though. As a local maximum at x equals negative 3. Do what we know first. And then to justify, well, the reason why we knew that was the case is since, now you might want to say, you might be interested in saying since f of x changes from increasing to decreasing, but that's not going to be acceptable as a justification. You have to refer to the first order. So since f prime of x changes from positive, you can use that abbreviation for positive, to negative, and then refer where that happens and switches specifically at x equals negative 3. In a similar fashion, we can justify the relative minimum at 3, so we can say f as a local minimum at x equals 3. And to justify that one, you can say since f prime of x changes from negative to positive at x equals 3. Take a look at one last example here. Again, a little more complicated. So let's go ahead and rewrite this first as x, and then 9 minus 2x to 1/2 power. So you can see to take the derivative here, overall we're going to need to use the product rule. So using the product rule, g prime of x, we have the derivative of the first one, which is just 1, times the second one as it is, 9 minus 2x to the 1/2, and then plus the first one as it is, x, times the derivative of the second one, and that's where we also need the chain rule, because we have a function inside, 9 minus 2x. So we use the power rule on the outside, do 1/2, 9 minus 2x to the negative 1/2. The chain rule says we have to multiply by the derivative of the inside, derivative of the inside, derivative of 9 is 0, derivative of negative 2x is negative 2, so multiply by negative 2. And then to simplify this, let's factor out the GCF. So you got this term and then plus this term. So what do they have in common? Well, they both have 9 minus 2x to different exponents, so we can factor it out to the lower exponent, which in this case is negative 1/2. So let's see now what's left of each term. Well, this had a 9 minus 2x to the 1/2. So the question is going to be 9 minus 2x to 1 power is going to be left. So one exponent and negative 1/2 would give you back 1/2. When you add those together, that would be 2/2. And negative 1/2 would give you back 1/2, but again, 2/2 is the same as 1. And since it's 1, well, we don't really even need these parentheses anymore. There's still so much. We need this parentheses here. We don't need this parentheses here. This is 9 minus 2x to the first, and there's nothing left to multiply by because it was just 1 there, and then plus from right here. Let's see what's left in the second one. The 9 minus 2x, so negative 1/2, that's gone. And actually, this negative actually changes that from a plus, it was, to a minus. The 2's reduce out, so those are gone as well, so all that's left is the x. And then we bring that to the denominator as the square root of 9 minus 2x. And the numerator we just have 9 minus 3x. We can make it even simpler by factoring out a 3. Leaves you with 3 minus x over the square root of 9 minus 2x. And now as a single fraction, you can find the critical numbers by saying the numerator and denominator equal to 0. So for the numerator, we get a critical number of x equals, you can say that goes over to x equals 3. And for the denominator, we set the 9 minus 2x equals 0. We add the 2x and divide by 2, so you get x equals 9/2. So those are our two critical numbers. Let's put them on the number line. If you got 9/2 is the same as 4.5, so 3 comes first, then 9/2. They move your number line, it's the first derivative. G prime x, 3 came from the numerator, so that makes the derivative 0. 9/2 came from the denominator, that makes the derivative on the top. So here we could test 0 there. 0 makes the numerator positive, denominator positive. Positive is positive. Between 3 and 9/2 is a small window. Remember, this is 4.5. 4 is probably the easiest thing to test. 3 minus 4 is negative. 4 in there makes it 9 minus 8. That's positive. Negative divided by positive is negative. And then over here, past 4.5, you test 5, makes the numerator negative. But if you test 5 in the denominator, now it's going to be 9 minus 10 is negative 1. But it's inside an even root of square root. So square root of a negative number, that's imaginary. So what that tells us is this over here, this interval doesn't even exist. It's like one of those danger domain problems where the function just ends. So this shows us that g of x is increasing and then decreasing, and then it just stops there. So in other words, the graph would look something like this. Increasing, decreasing, stops. And that's why the derivative wouldn't exist right there at the point, because you can't draw a tangent line there, and it wouldn't exist over here either. So at 3, you can see, first order change from positive to negative, then a relative max. But at 9/2, it goes from decreasing to nothing, right? So that's not a min or a max, relative min or max. So finally, we can say G has a relative maximum at x equals 3. And justify it in the same way, since g prime of x changes from positive to negative, but then you have to specify where that happens at x equals 3. And that concludes the notes for AP Calculus on the topic of relative and local extrema.